So many ramps, and this is not even all of them. Jeez. Hello yet again. Now, I just put out a video in the 32-bit series on the rearm board, which is a replacement for the Mega in your RAMPS sandwich setup. And I've gotten some questions about the 24-volt operations and backfeeding from the board. Now, a decent portion of this is going to be review from various videos in the RAMPS series, which you can go back and watch. I have it all on a playlist. 2 hours of raucous fun and laughs. Not really. It's a lot of techno babble. But I figured everyone's not going to watch that 2 hours, so the relevant stuff is here. Now, all these videos like this, I have time indexes in the video description below. And this is what you're going to see in that time index. So first thing we're going to talk about are the benefits of going to a higher voltage. Then we're going to talk about Ohm's law and how that applies to your connectors, your MOSFETs, and some math for the bed. Those are the big areas that we're talking about here. Then we'll touch on backfeeding versus USB or secondary power. Then we'll get into the actual mods. So we'll have the mods required for 8-bit Mega, the mods required for 32-bit rearm boards, miscellaneous DUA nonsense, and then we'll talk about some setups that don't require any mods or require few mods, that type of thing. And again, check out the time index. You can skip around and see what you want. Also, while you're down there, my support links are down. So if you want me to be able to afford to continue making these videos and continue to be able to afford to buy all these boards to break so that I can give you all information, yeah, just check out the support links below. But I'm going to kind of just ramble on this, and then I'll go back and edit it for coherency, and hopefully it's not too choppy. I move my microphone way down here. I have my camera up here set on autofocus, so hopefully like it focuses halfway decently. Seems to be doing it all right. Because I know it's really annoying when someone's like, Bert, focus. But anyways, I kind of was hoping I was finished with like the nuts and bolts of the RAMPS stuff, but here we go. It's the holidays. Here you go. It's a Christmas present for all of you. There we go. Stupid camera changing the freaking exposure. These were originally designed, as I said in the RAMPS overview video, for 12-volt operation using like what you have lying around. So generally that was just an ATX power supply from an old computer. It provides plenty of current, and the output happens to be 12 volts. So let's look at what the benefits of going to a higher voltage are. First off, you can get away with lower spec FETs and lower spec plugs, and that's because science, and we'll get into that. Consequently, that means less fire risk. You're going to get more torque from your motors. You're going to be able to run at higher speeds on your motors. You're going to get better performance out of your drivers. Now, not always, but particularly the Trinamics do not like running at lower voltage levels, and I'll talk about that a little bit. And it's possible to get faster and hotter heat up time on your various thermal pieces. That's not 100% the case. It depends what your cartridges are, but again, it's going to give us some more current headroom so we can run higher wattage stuff, and this is all because science. Now, I went through all the Ohm's law stuff in the MOSFET portions of the RAMPS series, but I have to touch on that a bit here because I know you're not going to watch that whole thing. But basically, if you're thinking your output is power, right, you have voltage and you have current, and they're like reciprocal of each other, more or less. So if you double the voltage that you're operating at, then you have the current that you're operating at. Specifically, this was all in that those stupid RAMPS connectors and why they melt video. And the problem with a lot of these boards that people were having is that either the connectors, so just these blue connectors or these pluggable green ones, were having problems with the current. Now, that's either because they were underrated. Some of these are, oh man, this is mirrored. That's really weird. So some of these are only rated at 10 amps, whereas like the bed polyfuse is rated at 11 amps, and then you might be pulling even more of that out of your bed. So some people are pulling up to like 15 amps off of their bed. Well, obviously, that's too much for the board. They shouldn't have done that, but they did it. And they're burning up their connectors. A second problem, like I talked about in the RAMPS series, was that people are not wiring these properly. Hopefully this cable is long enough to reach. Okay, there we go. So that's how I wire up these green connectors, and these are just the Euro pin terminals. And you put those on and crimp them, and then you have good contact between here. You screw this down nice. You don't have any frayed wires. Like I said in the video, don't tin these with solder, because then you're going to have problems with the two different metals, thermal expansion, you have creep, and you're not going to make good contact. So on our Ohm's law wheel, which I'm going to be referencing several times, we're down here in the power quadrant, specifically this equation right here. So for our case, we're going to have a relatively fixed current load, which is our bed or our heater or whatever. That's going to draw a particular amount of current through our connector. So we want low resistance, that's the Ohms sign for resistance, low resistance on our connector, because high resistance on our connector is going to turn the connector into a heater, which is not what we want. Now when you have like less contact area, you have higher resistance. More contact area is less resistance. Two things there. If you're making contact with just a little bit of it, or if you have like stranded wire and you're not, you're kind of like have this really sloppy connection like that, where you have strands all over the place, you're not using the full carrying capacity of that wire. You're increasing your contact resistance. It can take less current. It then in turn is dissipating more heat, and you're burning up your connectors. Alternatively, if that stays there for a while and you get a lot of heat and arcing or whatever, you're probably not arcing, but heat, you're going to get carbonized surface here, or just corroded surface. So you're going to raise your contact additionally because of oxidation or carbonization of your contacts. So make sure before you worry about blaming it on your RAMPS board or your connectors or anything like that, that you're not a bonehead and you're not plugging it in wrong. But a lot of the time it's because of substandard connectors. Now, the screw terminals, that's something that we can help ourselves by landing the wires correctly. These little friction terminals right here, they can also have band contact, or not be plated, or get corroded, or be made out of like a substandard material, and those will most definitely heat up and melt. But again, a lot of times that's because you're not respecting the rating of those terminals. So for instance, this one is 10 amps, which is pretty low. It's lower than our fuse, which is definitely not good. And unfortunately, that's all because of like penny pinching. But when you buy a RAMPS online, for example, this kit, it's hard to tell what they have spec'd on there. And again, that goes for just about any piece of electronics, really. And this kit right here, for example, this bed I happen to know draws way too much current for the connector that they sell it with. 24 volts can help that by not pumping as much current through these. So our equation for power, which is our heat that's generated, is going to equal current squared times resistance, and ideally we would want that resistance of the connector, Z in our case, to be 0. But the parts of that equation that we can change, even if we can't change the resistance of the connector, is the amount of current going through there. But if we want to generate the same amount of heating power in our bed or whatever, that means upping the voltage. Current's lower, voltage is higher. Cool? All right. Now let's talk specifically how that applies to your MOSFETs and the bed. I'll tie those two together. You know what? I completely forgot about the polyfuses. All right. Polyfuses are boring. Go back and watch the polyfuses and boredom video in the playlist if you're specifically interested about those. I'll talk about their ratings a little bit. Just make sure you drink a bunch of caffeine before you hit that video. And for more super nerdy details in this stuff, you can go back and watch these videos here. Just be aware that stuff gets a little bit mathy. They're not entertaining videos, they are informational. Basically what I did in that one was I pulled apart a bunch of these RAMPS boards, tested all the MOSFETs, and then gave them like kind of a pass-fail for 12-volt stuff, and rated them on a spreadsheet, and showed you the good, the bad, and the fake. Now, there are good fakes, like Deanna Troy's various hair extensions throughout the next generation, but we're talking about bad fakes here, like the special effects and whatever the heck was going on in this episode. I don't know what they were thinking. Yeah, you know what? I'm totally going to go watch some Star Trek when I'm finished here, and there's nothing you can do about it. But 90s television aside, what I did was I took a bunch of these MOSFETs and I cracked them open in a vise so that I could see the actual silicon dies inside. And you can see, obviously, these are all supposed to be the same. Yeah, not even close. Sometimes you can win the fake lottery and you get a better MOSFET, but a lot of times it's just a counterfeit that's a cheaper MOSFET that they put on there and silkscreen with the numbers that it's supposed to be. But the reason that I mention all of this is because we're talking about an RDS on, and that's going to rate relate again back to our power equation for Ohm's law, which applies whether or not the MOSFET is fake. And it also pertains to whether or not we actually are at the operating conditions where we hit the specs on the data sheet. So, okay, how does that relate to our bed in 24 volts? Now, very quickly, since I already hit this in the RAMPS series, let me run through an example for you. Looking at specs for our popular Mark IIB style PCB heated bed, usually that's going to have a resistance between 1 and 1.2 ohms, so we're going to take the higher one here. And then for our standard RAMPS 55NF06L MOSFETs, I found that most of them were a little bit high, like around 0.25 ohms, so we're going to use that value, and then just plunk that into an Ohm's law calculator here. This is why I put the time index. You can skip this, but our resistance is our bed value of 1.2 ohms, and then if we're talking about voltage at 12 volts, then we're assuming that's going to pull 10 amps, and the bed is going to be powered in 120 watts. Which just meets the specification of our 11 amp polyfuse. Now let's see what that does to our MOSFET. If we put in our RDS on of 0.025 and assume 10 amps sucking through it, that's going to be pulling 2.5 watts through the MOSFET. That's definitely higher than the free air dissipation rating, which is why at standard 12 volts and without, heat sinks and fans and all the kinds of things that people do to keep these cool, you typically get MOSFETs popping from time to time. Now, what happens if we go ahead and we change that to 24 volts and assume our 120 watt bed? Well, we're pulling half the current, 5 amps instead of 10 amps. Now, granted, that's not through the same bed, that's through a 24 volt bed that has a resistance of 4.8 ohms. Now, if we go ahead and say, okay, well, we have 10 volts that we could possibly do, what does that equate to with 24 volts? Well, this is where the heating up more and faster thing comes from, because you could run a 240 watt bed instead of a 120 watt bed. But then you'll be back to running your MOSFETs on the ragged edge, as well as your connectors and your polyfuse. So we know that we're going to be pulling like 5 amps at our same 120 watts for our bed. So if we put 5 in, and then we put the resistance of our RDS on of our MOSFET in, then we're not dissipating that 2.4 watts anymore. We're dissipating 0.025 watts on the MOSFET package, which is much more doable. And we do have MOSFETs that are better than that by a factor of 10. So if we get a much better MOSFET, we're not dissipating, just over half a watt. We're dissipating just under a tenth of a watt. And I did make a video on how to select the MOSFETs and where to source them back in the RAMPS video. So there you go. Now let's talk about powering our Arduino, backfeeding versus external power. Now, what we have to do is take our 12 volts from our RAMPS, knock it down to 5 volts for our Mega. And that's done through this pin right here, the D1 pin, which is consequently located here on the surface mount boards like the RAMPS 1.5, 1.6, etc., etc. So that takes 12 volts from your RAMPS power supply and it runs it into the regulator IC on the Arduino Mega. But there are other ways you can power it, as we see down here on the schematic, because we're taking that 5 volts that goes through a various different switching logic and then into our 3 volt regulator, etc., etc. So we can power it directly from the DC barrel jack, which goes into the regulator, or straight into USB, which is already 5 volts, so that just goes right to the IC. Or we can power the IC directly from our own regulated 5 volts. And finally, back powering like we do on the RAMPS is just putting power to this V-in pin that then goes directly to the regulator. Now, unfortunately, there's not an easy way to track down the bottom pins, even with all the open source stuff for the RAMPS, so I'll just show you that it's this freaking pin here. And that's the one that's going to be attached to our D1 diode, which we can see down here in the bottom left-hand corner of the RAMPS schematic, circled in purple, which is labeled AMVIN. Now, if you don't have a lot of experience with electronics and you're getting freaked out by like any of these schematic references, just go ahead and dive in. There's a lot of great sources online. I taught myself to read schematics when I was in middle school through Forrest Mim's mini engineer notebooks, which I would save up lawnmower jobs to go and buy, as well as Lloyd Alexander books. I mean, I spent my lawnmower money on Lloyd Alexander books. I did not learn to read schematics out of Lloyd Alexander books. I have no idea if you can read schematics. Probably not. But regardless, so the signal flow goes from our D1 diode, and that flows back into our pin right here on the Mega. That goes from the pin to the regulator IC right here that knocks it down from 12 volts to 5 volts, and then that goes out to power all of our peripherals as well as the IC and things like that. Peripherals like these full graphics controllers, which consequently draw a wee bit too much current sometimes depending on what else you have plugged in, and it can tend to overheat your Arduino's regulator and pop it. And that's why I'm talking about backfeeding to begin with, because Ohm's law, good old Jorg. Because in a land of like unicorns and puppies and rainbows and kittens and that types of thing, we would just be able to look at our data sheet and say, oh, we can put out 800 milliamps, no problem. And the regulators have an internal shutdown to protect the device from overheating. So even if we do draw too much power, it doesn't matter. Yeah, that's not the kind of world we live in, unfortunately, and some of our peripherals will draw too much current and overheat that because of the amount of voltage that we have to drop across it, particularly if they're not spec'd properly and you get something like a magnetic beeper instead of a piezo beeper that pulls much more current, etc., etc. So that's the whole backstory on why 24-volt mod usually includes removing the D1 resistor and then separately powering your Arduino. Because if a regulator dropping from 12 volts to 5 volts is bad under some circumstances, then dropping from 24 volts to 5 volts is terabad and will for sure blow it. All right, on to the actual mods. So first thing we'll talk about is the mods required for just our regular old 8-bit Arduino Mega setup. Now, what we primarily have to be concerned with in these mods are respecting the voltage ratings of particular components or the dissipation ratings of particular components. Specifically, our fuses or polyfuses, our capacitors, our backfeed power, and our LEDs to a lesser extent. So first off, the fuses. Now, if you see right here, it says 30 and then UF 900. That means it's a 30 volt compatible device and it'll run at holding current of 9 amps. So this one right here, fine for our 24 volt mod. We don't have to mod that. So best case scenario is to buy a board that already has either a fuse or if it has polyfuses, make sure it's rated at, 30 volts or more. But if they are bad for 24 volts, you can replace them, you can remove them and jumper between the holes, or you can just bridge them with a piece of wire and then make sure for both of those two final ones, you add an external fuse because you still need protection. And that can be something like this that's available at just about any automotive store, or something like this that's available at just about any electronics store. And those just go in line with your main power going into your green terminal block. Second is our capacitor ratings, which are printed right on it, usually. If it says 35 volts, obviously that's safe for 24 volts. It gives you a little bit of headroom, which is even better. If it says 16 volts, no bueno. You are going to pop them. And granted, that's not as bad as popping one of these capacitors, but it'll still ruin your afternoon, especially since they're surface mount. And just to quickly touch on the LED thing, this isn't like a make or break deal, but your board indicator LEDs, those little white rectangles, have a limiting resistor right here and up in the upper left-hand corner of your board as well. If they're over, 1.5K or 1.8K, you're probably pretty good. If it has 1K ohm limiting resistors on there, you might overheat your LEDs and pop them, which just means you won't have blinky lights on your board, which isn't the end of the world, but it is annoying. All right, so those first three were things you may have to deal with. This is one that you will have to do, and that's the backfeeding resistor. You're going to have to snip D1 resistor off, and then you'll have to power your Mega separately, which is not difficult. You could either do that through USB if 500 milliamps is enough. That's a no-brainer if you're using tether printing. You could also use the DC barrel jack input. That's fine as well. But just be in mind that there's a power sequence for logic and motor power for certain drivers, like Trinamics. So either goofy things or destruction can happen if you do that wrong. Now, version 2 of Vatarat's silent step stick protectors for Trinamics do have an additional diode that prevents that startup sequence from happening in the wrong order. So that's a good investment. They also allow more airflow underneath the chip to keep it cooler. But you can also hook up your power supply and for your RAMPS and your Arduino to a power strip and turn them on and off at the same time. Alternatively, you can wire some kind of step-down regulator that'll take the load off of the little tiny IC that's on your Mega board. So for example, if you knock down your 24 volts to like 7 volts and then backfeed it, you'll probably be fine. And again, that backfeed diode D1 is right here for a standard RAMPS 1.4, and for the surface mount RAMPS versions, it's right here by your input jack. It is not on those surface mount boards in the same position as D1 on the 1.4 boards. That's D2, which is just part of your reverse polarity protection circuit. So go ahead and leave D2 alone. All right, now let's talk about what mods are required for 32-bit rearm. Now, same mods as for Mega, except your backfeeding is fine. So make sure your fuses, capacitors, and LEDs are cool. If they're okay, no worries. You can just plug your ramps into your rearm, backfeed it from 24 volts, and hey, everything's peachy. So now let's talk about miscellaneous Dua stuff. If you did the Dua mods from either my Dua mod video or somebody else's, then the question is, can you backfeed from higher voltage into the Dua and be okay with the regulator? Now, I don't know exactly how much current these can take because they are a switching regulator. That's an improvement over the Mega. However, the capacitors are not rated very high. They're rated at 25 volts. So that's not a whole lot of headroom. I think I recommended in the video, just go ahead and don't backfeed it, power it separately. But if you were running like 18 or 19 volts, you could be fine. I gave no guarantees about that, and I didn't decide to go ahead and ruin a Dua to see if it worked. And now a little bit of like a bonus honorable mention mod. You can boost just the voltages you want to be at 24 volts and leave everything else alone. For example, with the standard RAMPS 1.4 boards, we have 4 connectors for our input, and they separate out the bed power from the regular power. So you can run just the bed at 24 volts, provided that your polyfuse for your bed is compatible with 24 volts, and you'll be just fine. Of course, you'll have to go ahead and use 2 power supplies so that you have like a 24 volt supply running, but you can also take a nice heavy duty voltage booster and run that off of your 12 volt supply. Alternatively, you can also run separate booster supplies to your step sticks themselves. Although if you do power your step sticks separately, make sure that you have decoupling capacitors for the power input pins for each individual node. Alright, so let's talk about those magical snowflake setups that don't require any mods at all for 24 volt. Well, going 32-bit and running a rearm board instead of a Mega, that is already ready to go right out of the box. And it's supported by Marlin 2, Smoothie, and Clipper, probably others as well. For 8-bit, there aren't really any magical unicorn setups except for like a Mega board that's been ruggedized with a better regulator, and those are unfortunately pretty expensive. But they do exist, so I figured I should mention them. And as far as RAMPS boards that don't need any mods for 24 volts, any of the surface mount stuff will work, like the 1.5, the 1.6, the 1.6 Plus, and these 1.6 are now open source, so you can use them guilt-free. The 1.5 is not, and it's not as good a board design, so you should probably steer toward the 1.6s. Because they have updated 4-layer board design, thicker copper traces, better connectors, as well as updated bed MOSFETs. And if you go back and look at my RAMPS roundup in comparison, you'll see that there are some magical snowflake boards that will run at 24 volts right out of the box. But unfortunately, you don't always really know what's going to show up. So make sure you have, a decent picture and a return policy for if they ship you something that's not like it is in a picture. But I didn't find any perfect ones. Like, for example, the Ziltech board, you have to replace the bed polyfuse, which isn't that big a deal, but everything else kind of works except for the bad MOSFETs. And then the Key Studio board, that was almost 100% ready to go out of the box, except they used the RAMPS 1.4a etch pattern from Robotal, which screwed up and bridged the jumpers, so you can't change the stepping mode. It's always completely on unless you want to go ahead and scratch the board traces out and use the jumpers. And before anyone asks, no, the RAMPS 1.4 SB premium boards are not 24 volt boards. The capacitors are rated at 25 volts, which just does not give you enough headroom to be safe. There you go. Definitive guide for 24 volt mods on the RAMPS. If you have any further questions, go ahead and leave them in the comments below. I try to get to as many of those as I can. If you're interested in this type of content, want to keep seeing me do it, check out my support links in the video description. Thank you very much, and until the next video, get out there and make something awesome.